Bismillahirrahmanirrahim. In the last video, we have discussed the PI compensation. In this, we are going to look at the lag compensation, which is the modified form of the PI compensation. In the PI compensation, we require an ideal integrator, and you have seen that we introduced the pole at the origin. Okay, so to implement the PI compensator, we need an active circuit which is based on op amps, and that integrator is susceptible to wind up. So instead of introducing the pole at the origin, we introduce the pole very close to the origin. So an alternative to the PI compensation is the lag compensation, and in this compensation the pole is placed near to the origin but not at the origin, because if we introduce at the origin, so the system will be susceptible to the integrator wind up. And if we introduce the pole very close to the zero, we can easily implement that compensator with the help of the passive components instead of using the active circuits based on op amps. So like PI compensation, lag compensation uses a closely spaced pole zero pair. We introduce the zero very close to the pole, as we did in the case of the PI compensation. And what is the advantage of introducing the zero? The angular contribution of the introduced pole is nearly cancelled out, and the transient response is nearly unaffected, because we are introducing the pole close to the zero to improve the steady state error in the response of the system. Another advantage of the lag compensation is that the type of the system is not increased. If we have the PI compensation, we introduce the pole at the origin, and because of that the system type increases by 1. But in the lag compensation, we are introducing the pole very close to the zero, right? So because of that, our pole will be somewhat like that, S plus let's suppose PC. So this is not at the origin, so system type is not increased because the type depends upon the number of poles at the origin. So if we introduce the pole at the origin, the steady state error will go to 0, can be made 0. But if we introduce a pole very close to the 0, the error is improved but not eliminated. You can say it is the disadvantage, but that helps us to implement the compensator easily, that if we introduce the pole very close to the 0, we can implement it with the help of the passive components. Okay, now let's consider a generic feedback system as shown in the figure. Here you can see the compensator, and here is the system. The system consists of number of zeros and the number of poles. And let's consider that it's a unity feedback system, then h of s will be equal to 1. So if it is a type 0 system, so for type 0 system, Pi will not be equal to 0, this one, because if any of this pole goes to 0, then that will introduce the type, it will become type 1 or type 2 system. So for all values of the I over here, you can see over here, this P cannot be equal to 0, right? So now what will be the position constant for this system? So position constant, as we have discussed in the previous video, is given by this equation, that is the limit s is approaching to 0 applied over the open loop gain. So open loop gain is this d of s into g of s into h of s. This h of s is equal to 1 and d of s is equal to k. So this can be written like that k into this transfer function. So now if we apply the limit, so all of these terms will become 0. So our Kp for the uncompensated system will be equal to k into z1 z2 divided by p1 p2 and so on, depending upon the number of poles and zeros. Now let's consider the compensated system, the system with the lag compensation. So this transfer function will not be simply k, rather it will be having a 0 and a pole that is introduced very close to the 0, very close to the origin in your S plane. So when we introduce this one, the system type will not increase. It is still 0 because we do not have the pole at the origin. And now if we calculate the compensated position constant, that is kpc, so that will be equal to k into z1 into z2 and so on, divided by p1 p2 and so on, into zc by pc. This zc will be coming from here, because if we apply the limit that this goes 0 and this goes 0, so zc and pc will appear over here. So your position constant will be modified by this factor, that is zc by pc, right? So we can write that this is equal to kpu, uncompensated position constant error, that is this one. So that will be updated by the ratio zc by pc, where zc is the 0 of the compensator and pc is the pole of the compensator. So the compensator pole is very close to the origin, then the compensator 0, so zc will be greater than pc, right? And because of that, your kpc compensated position constant error will be higher than the uncompensated error, and because of that, the steady state error of your system will be reduced, because we know that the steady state error is given by this equation for the type 0 system for the unit step input. So if you are going to increase the k, that is shown over here, so because of that your steady state error will be reduced. So if we introduce the lag compensation, the steady state error is reduced, and as zc is greater than pc, right, because we are going to introduce the 0 on the left side of your pole over the real axis, right? So the zc will be the position of the 0, and this is the position of the 0 and this one is the position of the pole, right? So zc is greater than the pc, so because of that your this kpc is greater than kpu, where c is indicating the compensated one and the u is indicating the uncompensated system. So your steady state error is reduced. To avoid affecting the transient response, what we require? We require that the 0 and pole are very close to each other. If they are very close to each other, this 0 will cancel the angle that is introduced because of this pole. So if this is the case, your transient response will not be updated, only the steady state error will be made 0 because of the effect of the pole that you are introducing very close to the 0. So as long as the zc and pc are very small, we can satisfy both requirement, that zc is quite large as compared to pc. It should be the case, because if it is the case, then your k will be increasing and the steady state error will be reducing, and we need that this pole is very close to the 0 is very close to the pole, so that the transient response is unaffected. So how we can get that one? Relative to the other poles of your system, if we keep this 0 very small and the pole position very small, that is if this is a very small value, let's suppose 0.005, and with respect to that this 0 is 0.05, they are quite small, right? And they fulfill both of these conditions, that zc is greater than pc, and they are nearly small with respect to the other position of the pole. If I say the other pole is, let's suppose, at s is equal to -5, so with respect to that they are very small, right? So they are nearly equal, and zc is large as compared to pc, so for that case your transient response will not be affected, only the steady state error will be compensated. And how much improvement will be there in the position constant or in the velocity constant or the static error constant, that depends upon the ratio of this zc and pc, because that you can see over here, your static error constant is updated by this factor zc by pc. So if the zc by pc is quite large, so your kpc will be higher as compared to kpu, that is uncompensated static error constant. So the steady state error will be reduced, because as k is increased, steady state error is reduced. So the ratio of the value of the gain required in the specifications and the gain found in the uncompensated system is the required ratio between the distance of 0 and pole from the origin, right? So now let's go through some examples for the more understanding of the lag compensator. So here you can see a system. It is the compensator with 1 0 and the pole, and this is our system. So we are going to design a compensator for 10x increment in the position constant. So let's suppose that we are going to introduce the pole in the compensator very close to the 0. So our PC is equal to 0.01, that is nearly 0. And what will be the position of the 0? The position of the 0 will be 10 times, because we need 10 times improvement. So we are going to improve the k by 10 times, and that is the ratio of the position of the poles and the 0. So ZC will be equal to 10 into PC, so that will be equal to zero point 0.1. So this will give us a 10x improvement, that is the desired one. So KPC, the compensated static constant, will be equal to uncompensated into the ZC by PC, so that will be equal to 10 times KP. So steady state error will be nearly reduced by 10 times. So now let's look at the root locus of the uncompensated and the compensated system. So if we do not introduce this pole pair, our root locus is like that, without the introduction of the compensator. But if we introduce the compensator, as we discussed above, so the you can see the position of the closed loop poles is slightly changed. But with the introduction of that pole 0 pair, here you can see the step response. This is the uncompensated response, right, this one. And this one is the compensated response for this input when we are going to apply the unit step input. So the uncompensated system have the very large steady state error, but the compensated system, here you can see the steady state error is going to reduce gradually. It is not going to become 0, because your pole and zeros are not exactly at the your pole is not exactly at the origin, but it's not a type 1 system, it's still a type 0 system. So there will be the steady state error, but that will be reduced, right? So with the introduction of the lag compensator, we have some steady state error, and it's easier to implement the lag compensator as compared to the ideal integrator that is at the origin. Okay, so now let's suppose that if we increase the ZC equal to 0.4 and we take PC is equal to 0.04, so what will be the response? Again, the improvement in the response of 10 times, because the ratio of these two, ZC and PC, that is equal to 10. So here you can see these are the desired closed loop holes for the certain value of the zeta, right? And if we introduce the compensator with this one, that 0 is at 0.4 and the pole is at 0.04, here you can see. So here you can see the step response for the system. So this is the uncompensated system, and this is the response of the compensated system. Okay, so still we have the steady state error that you can observe over here, a constant steady state error, but that is quite less as compared to the uncompensated system. So by the introduction of the lag compensator, you can improve the steady state error without significantly affecting the transient response of your system. Okay, so here are some steps which are useful for the designing of the lag compensator. First of all, draw the root locus plot of the uncompensated system whose open loop transfer function is g of s, and based upon the transient response specification, locate the dominant closed loop poles on the root locus. And what are those transient responses? Maybe based upon zeta, based upon the given natural frequency, you should select that what is the desired position of the closed loop poles, and then assume this as the transfer function of the lag compensator. This is the gain of the lag compensator, and this is the 0, and this one is the pole that is introduced by that one. So we can write this equation like that, that Kc into if we shift this beta inside, so s plus 1 by tau, and the beta if taken out from the and denominator, that will be cancelled out over here. So we can write this pole and 0 like this. Okay, so this is the transfer function of the lag compensator, and as the 0 is to be very close to that one, but on the right hand side of your pole, so this beta will be greater than 1. Okay, so now after this assumption, after defining the transfer function for the lag compensator, the next thing is to evaluate the particular static error constant that is specified in the problem, and then determine the amount of increase in the static error constant necessary to satisfy the specifications to improve the steady state error. How much increase in the particular constant static error constant is required, and then determine the pole and zero of the lag compensator that produces the necessary increase in the particular static error constant without appreciably altering the original root locus. Original root locus should not be changed, only the steady state error should be improved. So for that, the beta is basically equal to the ratio of the two constant that before uh, after compensation and before compensation. So that is kp compensated divided by the kp uncompensated, that is equal to beta. So after that, sketch the root locus plot for the compensated system and see that either your desired poles are at the root locus or not. Then you can fine tune the pole and zero position of your compensator, and you can bring the root locus at a position such that it passes through the point which are desired closed loop poles. Okay, and then you can adjust the gain k of the compensator using the magnitude condition so that the dominant closed loop poles lie at the desired location. So overall system is this one. Now let's see with the help of the example that how we can design the compensator. So consider an open loop transfer function which is given by this one for our unity feedback system, and if we write down the closed loop transfer function for this system, so that will be given by this expression. And if we look at the poles of the closed loop transfer function, so those are these one, two complex conjugate poles, and the one is the real pole over here. So these two poles, these are the dominant poles moving toward the infinity with the variation of the gain k at the root locus. So they will determine the transient response of the system and will also affect the steady state error. So these are the dominant closed loop poles, and marked over here. Now from here we can get the equation, characteristic equation of the second order, that is basically controlling the behavior of the system. So that can be written like that: the product of these two poles, this is the pole in the lower s plane, and this is the pole in the upper s plane. So simplifying this one, this is the characteristic equation, second order characteristic equation. And now if we compare it with the standard second order equation, we can say that omega n square is equal to 0.4532, right? And from here we can find out omega n, and the 2 zeta omega n is equal to this part. So from here the zeta will be equal to 0.4912, right? And if we want to look at the angle is equal to cos inverse of zeta, so that is 60.58. So here you can see the position of the closed loop poles for this particular system, uncompensated system. We have not compensated it yet. We have just looked at the position of the dominant closed loop poles in the S plane, and that is this one, that for the zeta equal to 0.492, and the angle will be 60.58. So this is the position of the closed loop poles. So this point is minus 0.3307, and this one is 0.4861 along the imaginary axis, because we have the poles over here for this closed loop. These are the closed loop poles. This is the real part, and this one is the imaginary part. So that is sketched over here. Okay, now let's look at the root locus of the uncompensated system. So that is sketched over here in this diagram. The transfer function is this one, g of s, that is equal to 1.06 divided by first of all we are convolving this one s and s plus 1 with the help of this one. This is the multiplication. The resultant will be multiplied with s plus 2. So we have this open loop transfer function, right? And then we are defining this transfer function, and then we are sketching the root locus of the system. Okay, and these are the instructions to limit the x-axis and the y-axis, and this is for the plot of the zeta line. So here we have plotted the zeta line 0.4912, right, at omega n 1, 2 and 3. Here you can see those circles. Omega n is equal to 1, 2 and this is for 3. Okay, so that is at this line your root locus is intersected at this position, right? So that is this one minus 0.3307, and the imaginary part is this one. This is one pole 1 over here, and the pole 2 over here. Those are shown over here, that if they are the part of the root locus, they will be at this position. Okay, now let's calculate the uh, static velocity error for the unit, let's suppose, ramp input that is applied to the system. So what will be the static velocity error? So that is given by s into g of s into h of s, open loop transfer function. So taking that, and so this and this will be cancelled out, and applying the limit, so that is equal to 0.53 per second. Okay, so now let's suppose that we want to increase this kV to 5 per second, because if we increase that kV, we know that the steady state error for the unit ramp input is equal to 1 by k v, right? So if we increase this kV, so definitely the steady state error will be reduced. So we have the transfer function of the compensator that is given by this equation. So rearranging this, we can write it like that, and this is the position of the 0, and this is the position of the pole, this one, right? So this is the position of the pole. So the ratio of these two is equal to beta, zc divided by pc. So that is equal to beta, and that is equal to the improvement in the uh, static error constant. So the improvement factor will be equal to new value of the kV divided by the old value of the kV. So we decided 5, and the previous one, the original one, is 0.53. So the improvement factor that is required is 9.43. So let's take that one equal to 10, and we design our compensator. So by taking beta is equal to 10, and we will have to fulfill these two conditions, that zc is quite large as compared to pc, and that we are getting by taking beta equal to 10, and they must be relatively small as compared to the other poles of your system. So other poles are at um, which position? One pole is over here, and the other pole is this one. So with respect to that one, if we take the position of the pole equal to, let's suppose, 0.005, so that is very small, right? And let's take zc equal to 0.05, 10 times higher than that one. So they are very close to each other, and the position of the 0 is higher as compared to the position of the pole. Okay, so our compensator transfer function will be this one, and now our loop will look like this. This is our compensator, and this is our g of s. Okay, so what will be the open loop transfer function? That will be obtained by multiplying these two together, this one and this one. So multiplying this one, we get this expression, and this can be written as this kc into 1.06, that is, let's suppose, equal to k. So k is equal to 1.06 into kc, and the rest of the transfer function can be written like this. Okay, now if we look at the we can, for the zeta 0.491, now we can find out the closed loop poles position over the root locus, and that will be this one. Okay, so now to find out the gain k at these closed loop poles, so we can use the magnitude condition, that we can set this open loop transfer function dfs into gfs equal to 1, and then we can take this s from the desired closed loop position. So for that, we can find out what should be the gain k. So that you can observe over here, right? That if we take if we take this s is equal to 0 point minus 0.31 plus 0.55j, that is one of the pole desired pole. So you will get k is equal to 1.0235. So you have obtained k from, and now you can find out kc. So kc will be equal to k divided by 1.06, right? So you can find out the compensator gain. So compensator gain will be k over 1.06. So compensator gain is 0.9656. So what will be the transfer function? Transfer function, as we discussed earlier, is given by this expression, right? Or it can be given by this expression, right? So using this expression, I can write it like that, that 0.9656 is the gain of the compensator, this is the position of the zero, this is the position of the pole, and in this form it can be written like this. And we can also write the transfer function of the compensator like that. Okay, so what will be the transfer function of the compensated system? The compensator transfer function multiplied with your system transfer function, you will get the transfer function of the compensator. So that is equal to this one, right? So this is the transfer function of the compensated system. Now if you look at what is the value of the static velocity error, so we can check it by this expression, that limit s is approaching to 0, s into g of s, g1 of s. G1 of s is the compensated system, right? So applying this limit, so this s and s will be cancelled out, and then putting these s is equal to zeros and simplifying it, so you are going to get 5.1175. So our desired goal, desired value of the kv was equal to 5. So we have the much higher value of the gain, so the steady state error will be reduced. So if you look at the unit ramp response for this system, if you apply this input unit ramp, and if you look at the uncompensated system, so this is the response of the uncompensated system, right? Over here you can see the difference is high as compared to this compensated system. The inner one, this one is the response of the compensated system when the kv is nearly equal to 5, and this one is when k is nearly equal to 0.5. So with this you can see the steady state error for the compensated system is smaller as compared to the uncompensated system because of the compensator that we have introduced. So let's conclude our video. We have discussed the lag compensator with the help of the example, and we have seen that in the lag compensation we introduce a zero pole very close to the origin, and we introduce a zero very close to the pole to cancel the angle that is introduced, but it helps us to improve the steady state error of the uh, in the response of the system. So that's all from this video. Thank you very much.